We aren't going to build a moon base by bringing materials from Earth. We're going to build it by cooking the lunar dust beneath our feet into glass and steel. Gravity is a tax that every space agency must pay, and the rates are exorbitant. To lift a single kilogram of payload from the surface of the Earth and place it onto the lunar surface costs approximately $1 million. Think about that for a second. A standard cinder block used in construction weighs about 17 kilograms. Sending just one of those blocks to the moon would cost $17 million. A small pressurized habitat would require thousands of them. This is the fundamental math that has kept humanity bound to low Earth orbit for decades. If we want to stay on the moon, if we want to build a permanent presence through the Artemis program, we cannot be shippers. We have to be miners. We have to be blacksmiths. We have to be masons. This is the story of the Dust Foundry. It is the engineering solution to the greatest logistics problem in human history. Instead of fighting the moon's environment, we are beginning to use its own chemistry against it. We are moving away from the era of bringing everything with us and entering the era of in situ resource utilization, or ISRU. At the heart of this revolution is a process that sounds like science fiction, but is grounded in pure electromagnetic physics: microwave sintering. We are going to 3D print our future in the stars, and we're going to do it using nothing but the dirt we're standing on and the invisible waves of the electromagnetic spectrum. To understand how we build on the moon, we first have to understand the material we are working with: lunar regolith. To the naked eye, it looks like harmless gray sand, but under a microscope, it tells a much more violent story. Unlike sand on Earth, which is tumbled by wind and water into smooth, rounded grains, lunar regolith is born from destruction. For billions of years, the moon has been bombarded by micrometeorites. Without an atmosphere to burn them up, these tiny rocks hit the surface at tens of thousands of kilometers per hour. They shatter the lunar crust into microscopic, jagged shards. This dust is composed mainly of silicates, oxides of iron, magnesium, and calcium. It is sharp, it is abrasive, and it is chemically reactive. Because it is constantly bombarded by solar radiation, it carries a static charge that makes it cling to everything, from spacesuits to camera lenses. But for an engineer, these properties are not just obstacles, they are opportunities. The regolith contains high concentrations of ilmenite, an iron titanium oxide. It is rich in silicon, and most importantly for our foundry, it is a dielectric material. This means it doesn't conduct electricity well, but it is very good at absorbing microwave radiation. On Earth, if you put a dry rock in a microwave, nothing much happens, but lunar regolith is different. Because of its unique composition, particularly the presence of nanophase iron, tiny particles of pure iron suspended in glass, it couples with microwave frequencies with incredible efficiency. When we hit this dust with the right frequency, the particles don't just get warm, they vibrate at a molecular level, creating internal friction that generates heat from the inside out. This is the core principle of microwave sintering. Sintering is not the same as melting. When you melt something, you turn it into a liquid, which is difficult to control in low gravity and high vacuum. Sintering is more elegant. We heat the regolith to just below its melting point, around 1100 to 1200 degrees Celsius. At this temperature, the atoms at the surface of the jagged dust grains become highly mobile. They begin to diffuse across the boundaries of the grains, fusing them together into a solid, ceramic-like mass. We are essentially turning dust into a synthetic stone, a lunar brick, without ever needing a drop of water or a bag of cement from Earth. Now, imagine this process scaled up and automated. This isn't just about making bricks in a kiln, it's about additive manufacturing on a planetary scale. NASA, through its collaboration with companies like Icon and the development of Project Olympus, is designing a massive 3D printing system that can operate autonomously on the lunar South Pole. The vision is a robotic gantry, or a specialized rover equipped with a high-powered microwave emitter and a regolith hopper. The process begins with autonomous rovers scooping up the surface regolith. They feed this raw material into the printer's head. As the printer moves, it lays down a layer of dust, and the microwave emitter follows, sintering the layer instantly into a solid floor. Then it lays another layer, and another. Bit by bit, the dust foundry builds up the walls of a habitat, a landing pad, or a radiation shield. Because the microwave energy penetrates the dust, the bond between the layers is incredibly strong, creating a monolithic structure that is far more durable than anything we could assemble from prefabricated parts.
But why go through all this trouble? Why not just use inflatable habitats? The answer lies in the moon's hostile environment. The moon has no atmosphere and no global magnetic field. This means the surface is constantly bathed in ionizing radiation from the sun and cosmic rays from deep space. To keep astronauts safe for long-term missions, we need shielding, heavy shielding. Calculations show that we need about 2 to 3 meters of lunar soil over a habitat to bring radiation levels down to Earth-like standards. By 3D printing these shells using microwave sintering, we create a pressurized, radiation-proof fortress. The sintered regolith acts as a thermal insulator, protecting the interior from the extreme temperature swings of the lunar day and night, which can range from 120 degrees Celsius to minus 170 degrees. Furthermore, these 3D printed structures are designed to withstand the impact of micrometeoroids. We are building the cathedrals of the 21st century, but instead of limestone and marble, we are using the debris of a billion-year-old cosmic bombardment. As of July 2026, the Artemis program is pushing into its most critical phase. We are no longer just planning to visit the moon. We are planning the Artemis base camp. The engineering challenges are immense. How do you power a microwave foundry on the moon? The energy requirements for centering large structures are significant. This is why the development of vertical solar arrays and small fission surface power systems is so vital. We need a constant, reliable source of kilowatts to keep the printers running through the 14-day lunar night. There is also the issue of lunar vacuum. In a vacuum, heat transfer is notoriously difficult because there is no air to carry heat away through convection. In the dust foundry, we have to manage the thermal gradients within the material very carefully. If the exterior cools too quickly while the interior is still hot, the 3D printed structure will crack due to thermal stress. Engineers are currently developing closed-loop feedback systems that use infrared sensors to monitor the temperature of every millimeter of the print, adjusting the microwave intensity in real time to ensure a perfect, stress-free fuse. This isn't just about building houses. The dust foundry is the first step toward a true lunar economy. Once we master the ability to sinter regolith into structural components, we can build more than just walls. We can build roads to mitigate the problem of dust kickup from rover tires. We can build landing pads that prevent rocket exhaust from sandblasting existing hardware. We can even begin to extract oxygen from the regolith during the sintering process. Many of the minerals in the lunar dust are oxides. If we heat them enough in the presence of certain catalysts, we can release the oxygen trapped inside. We aren't just printing a base. We are printing the very air the astronauts will breathe. The engineering philosophy of not magic is that there are no miracles, only solved problems. The dust foundry represents the ultimate solution to the tyranny of the rocket equation. We are learning to live off the land, much like the pioneers of old, but with the tools of high-frequency physics and robotics. We are moving toward a modular, scalable architecture, where the only limit to the size of our lunar city is the amount of energy we can harvest from the sun. Looking forward, the technology we develop from microwave sintering on the moon will be the blueprint for our journey to Mars. The Martian regolith is different, richer in iron oxides and containing perchlorates, but the fundamental principle remains the same. If we can master the foundry mindset on our own satellite, the rest of the solar system becomes accessible. We will no longer be guests in space, we will be residents. As we stand here in 2026, the first robotic scouts for the dust foundry are already being tested in simulated lunar environments on Earth. High-fidelity regolith simulants, created to match the jaggedness and chemical profile of Apollo samples, are being fused into structural beams in vacuum chambers. The data is clear. It works. The physics is sound. The engineering is being refined every single day. The moon is no longer just a destination for flags and footprints. It is a construction site. It is a laboratory. And most importantly, it is a source of raw material. We used to look at the moon and see a barren, desolate rock. Now, through the lens of modern engineering, we see a vast, untapped warehouse of building materials.
We are going back to the moon, and this time we are bringing the Foundry with us. The transition from Earth dependence to lunar autonomy is the most significant hurdle in the history of space exploration. It requires us to rethink everything we know about construction. On Earth, we build against gravity. On the moon, we build with it. On Earth, we fight the elements. On the moon, we use the elements as our primary resource. The microwave sintering process is the bridge between these two worlds. It is the tool that turns a hostile environment into a habitable one. When the first permanent residents of the Artemis base camp look up at the walls of their habitat, they won't see a structure that was flown in on a rocket. They will see the very ground they stand on, transformed by human ingenuity and the precision of Maxwell's equations. They will see a testament to the fact that we don't need magic to conquer the stars. We just need better engineering. The dust foundry is more than a machine. It is a symbol of our maturity as a spacefaring species. It represents the moment we stopped asking, what can we bring to space, and started asking, what can we make in space? As we continue to refine the microwave sintering process, we are laying the foundation for a future where humanity is not confined to a single planet. We are building a world out of dust, one layer at a time. In the coming decade, we will see the first 3D printed landing pads at the lunar South Pole. We will see the first sintered roads connecting the gateway's lunar downlinks to the mining outposts. And eventually, we will see the first cities, not built by thousands of workers, but by a fleet of autonomous rovers, quietly cooking the lunar surface into a home. The math is simple, the physics is proven, and the engineering is well underway. The moon is ready, the foundry is heating up, and the future is being printed as we speak.